Hello everyone, welcome to Linear Algebra for Data Science and Machine Learning. In this course, we will cover why learn linear algebra, and then sets, linear equation systems, what's a scalar, scalar and vector arithmetic, vector addition and subtraction, scalar multiplication of vectors, dot and cross product, dot product with linear algebra style, vector subspace, linear combination of vectors, span, linear dependence and independence, solving systems of linear equations, linear equation example, generating set and basis, linear mapping, linear transformations, additivity, homogeneity and kernel, matrices and tensors. Then we will continue with matrix multiplication, range of a matrix, kernel of a matrix, determinant of a matrix, identity, transpose, and inverse matrices. And then finally, we will finish with Eigenvector and Eigenvalue. Now let's answer the question, why learn linear algebra? There are four main things that you need to know. These are linear algebra notation, linear algebra arithmetic, matrix factorization, and linear least squares. You will need the notation to write algorithms and to also read algorithms. They will have the same notation as this course because there's a standard notation for vectors and matrices, and everyone follows that notation. You need to know how to do arithmetic because you need that to process data, and your data will be in the form of a matrix, and you will use vectors to analyze them. You also need matrix factorization. It is necessary for doing operations with higher order matrices, and we will learn about these in this course. And linear least squares. This is a necessary tool or a necessary skill for creating machine learning models. And here we have an example of creating a machine learning model. We have our data and we enter it and represent, prepare, model, search, and visualize. For example, while preparing our data, we will write it in a matrix format, and we will do various operations to make it more meaningful, and then we will write functions with our data. We will model our functions. We will have an input and an output, and this is directly related to linear algebra. We will have an image, we will have a domain, we will have a value that's mapping to another value. And here we have another real-life example. Your computer screens or phone screens are also using linear algebra because every image you see is in the form of pixels, and those pixels are organized in a matrix. For example, on the right, we have 22 rows and 33 columns, and as you can see, all of these rows or columns are holding pixels. And when you do operations with those columns or rows, you can change how images look. And when you have more rows and columns, you have higher resolution. For example, on the left, we have the Wikipedia image, and it has clearly more rows and columns, so it has higher resolution compared to the image on the right. Now let's start with sets. Sets are a collection of objects. These objects can be anything. They can be numbers, words, characters, or shapes. For example, we have Z. Z is a predefined set that everyone agrees on. Z is the set of all integers from negative infinity to positive infinity. So the numbers like negative 10, 0, 5, 200, numbers without decimal points. And we also have set of letters in an alphabet. And here we have numbers on the set of integers, and on the set of letters we have letters. And there is a fundamental difference between those two sets. For example, the set of all integers is infinite, but set of letters in the alphabet is a finite set. We can also have set of nationalities in a group of friends. You can have an American, Canadian, Dutch, German, or Indian, Chinese, any group of friends. You can have people from multiple nationalities, and if you write everyone's nationality in a set, you can also create a set. Here we have an example of set and mapping. we have one set on the left and another set on the right, and we are mapping from one set to another. And if you don't know what mapping is, don't worry, because you will learn about mapping right now. So when you have two sets, and when an element from set X or set A corresponds to an element in set Y, that's called mapping. For example, the element X is mapped to a specific element on the set Y, and it's mapped to a function. So the image on the right is called the image set, and it is f of x. So the function of x, you put x value in a function that gives you a value, and that value is what the x corresponds to. And we will do more examples with mapping and function, numerical examples in the future. Here we have an example of sets. We have temperature and ozone. Here we have set of temperatures and set of ozone, and we are mapping them. So we have the temperature, ozone. We look at the correlation and graph the correlation between the temperature and ozone, and look at how one changes the other. For example, when we go from 60 to 90 on the temperature scale, from the ozone scale they go from 0 to 150. And on the right side we have a more coding example. We have input, hidden, output. That hidden will be our process. This is what our model will do. We will have an input. We will do some operations and algorithm with the input, and the result of that algorithm will be an output. And if you ignore hidden, because it doesn't matter, the only thing that matters is the input and the output. When you write code, the algorithm or the hidden matters, but there are different ways of getting the output from the input. We will define hidden, and we will try to get a meaningful output from our input. And we have linear equation systems. Let's say that we have the equation 2x plus 5y is equal to 15, and we have 2x minus 3y is equal to 10. And we can solve this equation by doing the first equation subtracted from the second equation and solve for the y. And this is what you learned in high school or in middle school, depending on the country that you were educated in. But instead of doing that, we can also use linear algebra notation. For example, we can write x and y as a matrix, and we can write the coefficients. We can write x and y as a vector and write the coefficients as a matrix and the output as a vector as well. And we can do matrix vector multiplication, which we will do. This is just an example of how the simpler things create more complicated examples. And we have a direct application of it. We have the input x, and we have the weight w, and this is a linear equation, and we are doing linear multiplication to get our output. And in our courses we will learn all about machine learning after learning about the math behind it. Now let's answer the question, what's a scale? It's an object with only a magnitude. For example, you can have 5 kilograms of apples, you can have $10, or you can run at, I don't know, 10 meters per second. And all of these values only have magnitudes, and they don't have a direction. They just scale something, and this is all they do. And you know scalar arithmetic, it's regular math. You have 5 plus 5 equals to 10, 5 times 2 is equal to 15, 20 over 4 is 5, 15 minus 10 is equal to 5. These are regular numbers, they only give a magnitude. But vectors are different. They are objects with a magnitude and a direction, and because of that direction, the math behind them is different. For example, instead of 5 kilometers per hour, we have 5 kilometers per hour due east. We have a direction. And on the coordinate plane, you can see that vector. Vectors are usually shown with arrows. The length of the arrow is the magnitude, and you can see the direction. Here it is due east or due x direction. And we have norm of a vector. This is a fancy way of saying the length. And we have two different norms. We have the type 2 norm. We have x squared plus y squared in square root. So our x magnitude is y and our y magnitude is y. And on this specific example, our vector's length is equal to 4. So this equation, 4 is equal to square root of x squared plus y squared. And as you can see, anywhere on that circle, this equation will hold true. Because the distance from the center of the circle is always the same to the side of the circle itself, the circle. So you have the radius 4, and you rotate that line 360 degrees, and that gives you a circle. This is the type 2 norm, and this is the more common norm that people usually use for different purposes. But for machine learning, we also have type 1 norm, and instead of a circle, this one gives you a square. Here we have absolute value of x plus absolute value of y is equal to 4. And anywhere on those squares, so any point on that square will hold this true. So for example, when we have the intersection of the circle and the square, we have x is equal to 4, y is equal to 0, and that's true. But if you look at the value for the diagonal vector, and if you look at the value that it's intersecting with the square, we can see that this looks like a 45-degree angle between the vector and the x-axis and the y-axis. So we can see that the point there is 2 and 2. So x is 2, y is 2. The total value is equal to 2. And if you look at the fourth quadrant, so to the bottom right, our x is 2, our y is minus 2. If we look at this point here, and that gives us 2 plus absolute value of minus 2, which is equal to 2, and it gives us 4. And we have vector arithmetic. Vector arithmetic is different from scalar arithmetic because vectors have directions. We can add vectors, we can subtract vectors, and we can also multiply vectors with each other. And this is different from scalar arithmetic because of the direction, and we will have to consider the direction while doing arithmetic with vectors. Now let's continue with vector addition and subtraction. Let's say that we have vectors a and b, and we have x, y for vector a, and we have q and w for vector b. And we can visualize them here. We have vector a and vector b, and let's say that we want to add those vectors. We put the end of 1 to the initial point of 1, and we put them together, and then connect the starting point and the end point, as you can see here. So we have the starting point of A connecting with the starting point of B, and then we have the end point of B. And after connecting that, we connect the end point of B with the starting point of A. And it doesn't matter if you do A plus B or B plus A. Same with regular arithmetic with scalars. The order doesn't matter. You can have vector ABC and vector A plus B plus C is equal to A plus C plus B or C plus B plus A. And you can also find this numerically. So let's say that we want to do A plus B. We would do Q plus X or X plus Q. It's the same because we are adding the X coordinates, then we add the Y coordinates, y plus w will give us the new y value. And if you want to subtract vectors, it's the same, but you reverse the direction. So instead of connecting A and B, you would change one of them's direction. So you would connect the end point of B the same way, but you would rotate it 180 degrees. And when you want to do it numerically, you do x minus q and y minus w, and with subtraction the order matters. A minus b is different from b minus a. And you can also multiply vectors with scalars. This changes the magnitude and also may change the direction based on the value. For example, let's say that we have the vector a and we multiply it with 2 and we get the vector 2a. This vector is multiplied with a scalar, so the direction doesn't change because the sign is the same and the magnitude is doubled. If you multiply the vector a with -1, you change the direction, so -a has the same magnitude but in the opposite direction. And the same for -2a. It is in the same direction with -a or the opposite direction of 2a, and it is to the left. And the positive and the negatives depend on the initial direction that you define them. For example, if the a vector was up, negative a vector would be down. This is fairly simple but important. Let's look at a machine learning example. We have an input and we have a weight. Our input is a vector, the vector x. It has x1, x2, x3 up to xi, and we multiply them with our weight and then we add our bias to get our output. And now let's continue with multiplying vectors. First, we have the dot product. Dot product is very important and it gives you how much two vectors are pointing in the same direction. So the answer can be 1, answer can be 0, answer can be -1, or any value that depends on their length. For example, here we have the vector orange and vector blue, and in the first scenario we have orange vector and the blue vector are pointing in the exact same direction. So the dot product is length of O times length of B and cosine alpha. As you can see here, alpha is the angle between them. And in the first example here, the alpha is equal to 0, so the cosine 0 is equal to 1. So the dot product is equal to the scalar product of their length. And here we have the same vectors, but they are pointing in the opposite direction. Here, dot product has the same magnitude, but in the opposite direction, where they are pointing in the opposite way. And two vectors are perpendicular or orthogonal. The dot product is equal to 0 because they are not pointing in the same direction in any way. You can write vectors in different components, and all the components of orange are in totally different directions than all the components of vector blue. And look at the example with alpha. Here we have the blue vector and the orange vector pointing kinda in the same direction. And if we wrote the blue vector as an addition of two vectors, one pointing up and one pointing right, we would get the dot product. That's where the cosine part comes in. We check the direction of the vector that's pointing in the same way. And this is very useful in machine learning. And we can also do the same thing with linear algebra style. We have the vector vx and vector vy, and we have the coordinates x1, x2, x3, x4, the infinite, and we want to get the dot product. As you know, dot product is a scalar value, although the inputs are vectors. So the dot product is equal to x1 times y1 plus x2 times y2, x3 times y3, x4 plus y4. For example, if we had two orthogonal vectors, 1, 0 and 0, 1, we would get 0. So we have 1 times 0, 0, and 1 times 0 is also 0, 0 plus 0 is equal to 0. And you can try it with any orthogonal vectors. You can try any numbers you want on the coordinate plane, and if the vectors are perpendicular, their dot product will be always 0. And here we have a machine learning example. While creating the convolutional neural network, we perform the dot product between the input layer and the convolution layer. And it's okay if you don't understand what that example is. We will learn all about this in the future in our other courses. And now let's continue with cross product. Unlike dot product, the result of a cross product is also a vector. And as you can see in this image, you have two vectors, VA and VB, and they are creating a plane, a two-dimensional plane. So we have vector A and vector B. We can add them up and we can get a parallelogram or a shape like that, and depending on their shape, it can be a rectangle or a square as well. And we have the cross product that's perpendicular to that. So the cross product gives you a vector that's perpendicular to the plane that the original vectors create. And the length of this vector is equal to the area of that shape the vectors create. For example, we have VA, VB times sine theta. Theta is the angle between the vectors. And this gives you the geometric area of the plane that, or the shape that the vectors create. And that's the length of the cross product. And every time, in every cross product, the direction of the cross product is perpendicular to the set plane. And we have normalizing a vector. This gives the vector that has the same direction as the original vector, but the length is equal to the unit vector. And on a regular coordinate system, our unit vectors are 0, 1 and 1, 0. And you can get every vector by altering and adding those unit vectors, and we will do more with unit vectors and getting vectors by using other vectors. Let's look at this example. We have the vector 4, 3, so the x dimension is 4, the y dimension is 3, so our magnitude is 5. Our magnitude is equal to the 4 squared plus 3 squared. 16 plus 9 is equal to 25. Root 25 is 5. And we divide our vector by its length. This bars here, the absolute value bars, when you are writing a vector, gives you the length. So we have 4 and 3 over 5. And we can write this in vector notation. So we have 4 over 5, comma 3 over 5. Normalizing is used for k-nearest neighbor algorithm. For example, we have this green dot here, and we want to look at the 3 nearest neighbors to that object. And we have 2 reds and a blue here. And if you look at the nearest 3, the smaller circle, we can see that the ones that are nearest to belong to the class that are red triangle. And if we didn't normalize this data and run our Kernel algorithm without normalizing it, we might get an error, and because of that, we normalize our data first. Because of this, normalizing is used for this algorithm and many other algorithms, because if we don't normalize our data, we are very likely to get errors. And now we can continue with vector spaces. This is a very important part of linear algebra. Vector spaces are a collection of vectors that define addition and multiplication. For example, we have the vector space R2, which has vectors with x and y values as any real numbers. For example, we have vy here and vx here, and those are basis vectors we will learn soon. You can write all the vectors in a vector space by using two vectors if it is an R3, or if it's an R2 you can write all the vectors with two vectors. If it is an R3 you can use 3, or with various other combinations. And now let's continue. They don't have to be two-dimensional. You can have multiple dimensions. You can have 3 dimensions or 4 dimensions, 5 dimensions, 6 dimensions, infinite dimensions. And this will be very useful while writing our machine learning algorithms. For example, on the right we have a vector space that has 3 points. We have x, y, and z. So we have the x dimension, y dimension, and the z dimension. And we also have vector subspaces. As I said earlier, vector subspaces are a collection of vectors, and you can think of them as sets, great or huge sets, and they can have smaller sets in them or smaller subspaces. For example, let's look at the equation on the right. We have that 5x minus 3y is equal to 0, and the x and y are real numbers. And we have the smaller set here with 0 vector, v1, v2, v3. You can think of the 0 vector as the algebraic 0. If you add a vector to the 0 vector, you get your original vector. And if you do the product of a vector with 0 vector, you get 0. Now let's look at our vector space to see if it is defined or not. Now let's check if this is a vector subspace. There are 3 conditions. First of all, the 0 vector of the greater space must be included in every subspace. So our subspace S must have the same 0 vector as the greater space V. And to check that, we put our 0 vector here, which is 0, 0. And when we put our zeros here, we have 5 times 0 minus 3 times 0 is equal to 0. That checks. So we can conclude that our 0 vector is included in this vector subspace. Now we need to check for addition. What I mean is that we have v1 and v2, and when we add those two vectors together, their sum also must be in this vector subspace. So let's say that you have vector A and vector B, you add them up, and their result must be in the same vector subspace or vector space as the vectors that created that. They cannot exceed or go beyond that space. And let's check for addition. We have x1, y1, x2, y2. We add those two vectors together, and we know that x1, y1, x2, y2 are real numbers, and we know our condition here, 5x minus 3y is equal to 0, and we can put our resulted vector to our equation. We have 5x plus 1 plus 5x1 plus x2 minus 3y1 plus y2, and that must be equal to 0 for the 0 vector, and we can multiply with 5 and 3. We have 5x1 minus 3y1 plus 5x2 minus 3y2, and we know that this checks out. We can just put 0 for x1, x2, y1, y2, and we know that they are real numbers, so our summation is included. Or we can write different values. For example, we can say that x1 is 1 and x2 is minus 1, and we get 0. We can say that y2 is 2, y1 is negative 2. You add them up, you get 0, and 5 times 0 is equal to 0, 3 times 0 is equal to 0, 0 minus 0 is equal to 0. This is how you check for addition. And it also must be multiplicative. So if you multiply a vector with a scalar, the resultant scaled vector also must be in this vector space. or vector subspace. So we have x and y, and we multiply it with a, so we get ax and ay. And when we write our x and y, so the equation 5x minus 3y equals to 0, we get 5ax minus 3y is equal to 0. We can take a out of the equation and we can write 5x minus 3y equals to 0. We know that 5x and 3y are real values, and we can find infinite number of real numbers that satisfy this equation. So we can conclude that this vector subspace has a zero vector, is additive, and is also multiplicative. So it's a real vector subspace. And this is used for random forest. This is a sampling machine learning algorithm, and as you can see, we have multiple trees, and those trees also have subtrees. In random forest algorithm, our forest is created by training decision trees for multiple subsamples. Our samples are our data, and we have different trees here. We have tree 1, tree 2, up to tree n. We can have infinite number of trees, or not infinite, but a lot, and we use those trees to create our forest and create our machine learning model. And this is an example of vector subspace. We can think of our data as vectors, and from them we create a space. And we can continue with linear combinations of vectors. This is one of the fundamental topics in linear algebra, and this will be very used. From the rest of this course, in every slide, we will do linear combinations of vectors. In our vector addition and subtraction slides, we did linear combinations of vectors in a very simple way. This is simply writing a vector by using other vectors. We scale different vectors and we add them up to get a third or fourth vector. And you can combine infinite number of vectors to get the vector that you want. Now let's do an example. For example, we have the vector 5 and 3, and we have v1, 20 and 3, v2, 0 and 6. And let's see if we can write the vector v as a linear combination of v1 and v2. So we are trying to see if we can scale v1 and v2. If necessary, then add them up or subtract them, which is actually the same thing, it's just the different sign, and get 5 and 3. So we want the x is equal to 5, so we do 5 is equal to 20a plus 0b. You can use different letters. For example, you can do 5 alpha or 0 beta, any coefficient that you want. And we write the x value, so 5 is equal to 20a, and for our y's, we want to get the value 3, and our v1's y value is 3, so we have a times 3 plus b times 6 is equal to 3. And we check if we can get a value and b value, and we get 1 over 4 and 3 over 8. We can just do 20 and 5. They cancel out. We get 1 is equal to 4a, and we get a is equal to 1 over 4. Then we plug that value here. 3 is equal to 3 over 4 plus b times 6, and our b is 3 over 8. And as we got those values, we can say that v is a linear combination of v1 and v2. And now let's learn about span. Span is very similar to linear combinations. These are the vectors that you can get by using one or more vectors. For example, we have vy and vx, 0, 1 and 1, 0. And by scaling them with any real number, you can get all the vectors in R2. For example, in the previous slide, we had 5, 3, 23, 0, 6. And as you can see, you can get all of those three vectors by scaling and adding Vy and Vx. Let's do a simple example. For example, our V1 is equal to Vy times 5, so 0, 5. We scaled our Vy to get V1, and we scale Vx to get V2. So just multiply it by 3. We have 3 and 0, 0 and 5, and we can get V3 by adding V1 and V2. We get 3 and 5, and as you can see, this is a linear combination of Vx and Vy. We can write V1 plus V2 is equal to V3, or we can also write 3Vx plus 5Vy is equal to 3 over 5. And that leads us to linear dependence and independence. Let's say that you have a set of vectors, and all of these vectors are either linearly independent or dependent. So we have V, and we have A, B, C to N, and we also have n number of vectors. We can say that these vectors are linearly independent if you get the 0 vector only when all the coefficients are equal to 0. And by doing that, if the coefficients A, C to N, if they are not 0, you can't get the 0 vector. This shows that you cannot get one of the vectors in that space by combining other two vectors. For example, let's say that we want to get V3, but we can't get V3 by combining every other vector. And because of that, we can say that they are linearly independent. Now let's look at this example. Let's check if V1 and V2 are linearly dependent or independent. Our set only has two vectors. Let's see if we can get the 0 vector. So our 0 is equal to A times 20 plus B times 0, and A times 3 plus B times 6 is also equal to 0. For this to be true, our coefficients A and B has to be equal to 0. So we can say that these two vectors are linearly independent. And if we had, for example, the vector 0, 1 here as our V3, these vectors would be linearly dependent, because then we would be able to get V2 as a combination of V1 and V3. We could write 0V1 plus 6V3, and 6 times 0, 1 gives us 0, 6, that's V2. And this is very common in machine learning algorithms. In a linear regression algorithm, features are independent variables, and the output is a dependent variable. Linear regression is a linear approach to model the relationship between a scalar response and one or more explanatory variables. So what I mean is that we have the variables x1, x2, x3 to xp, and we have the dependent variable y, and you can see that our y value is a line, and we know that we can write lines as vectors. So from those dots we get a vector, and this is very commonly used in data science and machine learning. Knowing how to solve systems of linear recursion is a necessary skill, and you can solve them by putting them in row echelon form or upper triangular form. And when you put the values in that form, you can simply use like substitution and get every value that you need. For example, let's say that we have a plus 3b minus 4c plus 2d is equal to 5. Then we have b plus 3c minus 2d is equal to 1. c plus 4d is equal to 2. And then 2d is equal to 6. From this we can get that d is equal to 3. Then we plug it, get a value for c. We have 4 times 3, 12. So 12 plus c is equal to 2. So we know that c is minus 10. Yes, and then from that we can get b, and then we can get a. But usually your values won't be in this form, and we will have to put them in upper triangular or row echelon form. So let's say that we have 2a plus b plus c equals to 5, and we also have 4a plus b plus 3c equals to 2, and 6a plus b plus 4c is equal to 0. As you can see, we have 3 equations and 3 unknowns, so this system is solvable. First we do -2 row 1 plus row 2 is equal to the second row, and we multiply the first row with -2, we get -4a, -2b, -2c, and we get -10. And then we add that to the second row, we get 0 minus b and plus c. And this is equal to 8. And every operation that you do to the left side, you also need to do to the right side. Because if you do it to only one side, your equation will not be solved, or if you get a value, your value will be incorrect. And now on the second row, we have only 2 values, so we are getting closer to the form that we want. Now we want to get only the c in the third row. And to do that, we do -3 row 1 plus row 3 is equal to row 3. So we get 2a plus b plus is equal to 5. Row 1 stays the same. Row 2 stays the same. 0 minus b plus c is equal to -8. And on the row 3, we get 0 minus 2b plus c is equal to -8, -15. And we get that by getting -6a minus 3b minus 3c is equal to -15. This is row 1 times 3, and then we add row 2. It's closer to the format that we want, but it doesn't exactly work right now. We have b and c, but we can solve this. We can cancel the second b in the, or the 2b in the third row. To do that, we multiply the second row by -2 and add that to the third row and make that the new value of third row. And after doing that, we get -c is equal to 1. And if we multiply both sides of the equation, we get that c is equal to -1. And then we plug that to the second row. Because c is -1, we can do -7 is equal to 2b, so b is equal to -3.5. Then we can put the b value and the c value to the first row and get a and get the solution for our linear equations. I will skip that for now. You can find a yourself. It's really trivial. And now let's continue with generating set and basis. This is similar to linear dependence or independence, or not similar but related. If any vector in V can be written as a linear combination of vectors in the subspace S or the set S, we can say that that subspace or that set of vectors is the generating set for the space V. And if the generating set is linearly independent, it's called a basis. So think about R2, and we have 2 common basis vectors for R2. These are 0, 1 and 1, 0. Any vector like 5, 10, 220, pi and e are all of them, every vector with real y and x values are just 0, 1 and 1, 0 scaled with a real number. And because of that, we can say that these vectors are the basis for R2, and they are not the only basis vectors. We can have a different set with different vectors, and they could also be the basis for R2. Or if our generating set has different vectors, for example, our generating set has maybe v1, v2, and v3, then they could be the set that create R3, for example, or R4, or a different subspace or a space. And the basis also has v0, because we know that any subset or the subspace has the 0 vector as well. Now let's do an generating set example. Let's say that we have v1 and v2, and let's see if we can get every vector in R2 by using those two vectors. And we will be able to get every single vector in R2 if these vectors are linearly independent. If they are linearly independent, we can scale them with different real values and add them up, and their combination would span all of the vectors in R2. So to prove that it is a basis for R2, we have to see if they are linearly independent or dependent. So we have 0 vector is equal to av1 plus bv2, and we have negative 3a plus 6b that's equal to 0. Those are the x values. And we have 5a plus 7b is equal to 0 as well. That's for the y values. And if only a and b values that satisfy those equations are 0, we can say that they are linearly independent and they are the generating set, or a set that includes v1 and v2 is a generating set for R2. And from this we get a is equal to 2b from the first equation, and when we put that into the second equation we get 17b is equal to 0. So b is equal to 0, and because b is equal to 0, a is also equal to 0, so we can conclude that these two vectors are linearly independent, and because they are linearly independent, set S, which only has v1 and v2, is a generating set for R2, and it's also the basis because it's linearly independent. You can see the linearly independent here. It's just to rewrite or re-show that. Now let's continue. We have linear mapping, linear transformations. Because we are learning linear algebra, everything is linear, so that means that additive and homogeneous. We have the set A and set B, and every vector in A corresponds to a different vector in B. And because we are learning about linear algebra, as a rule, for a transformation or a mapping to be linear, 0 vector in one set or one space must map to the 0 vector in the other. So the 0 vector in A is mapping to the 0 vector in B. And we have A1 that's mapping to B1, A2 mapping to B2, A3 mapping to B3, and here every value is mapping to a single one, but this doesn't have to be the case. We could have VA1 and vector A2 mapping to the same value. Now let's continue with additivity. This is the rule for being additive. So let's say that we have vectors VA and VB, and they're in the space V, and we have a linear transformation. This equation must hold true for a linear transformation to be additive. So we have the vectors A and B, and let's say that we get B3 when we add them, and the transformation of the combined vector must be the same as transforming the vectors separately and then adding them. Let's do an example so you can see it clearly. We have xy, and the vector xy is mapping to the vector 2x plus x plus y minus x minus y. So let's see if this mapping is additive, let's get LVA plus VB. So we have VA and VB. We have A1, A2, B1, B2. Let's add these vectors first and then linearly transform them. So we add VA and VB. We get A1 plus B1 as our X and A2 as B2 as our Y. Then we linearly transform this based on the rule above. Our X is 2X, Y is X plus Y, and our Z is X minus Y. We get 2A plus 2B just multiplied by 2, and with X plus Y, so with A1 plus B1 plus A2 plus B2, and we also have A1 plus B1 minus A2 minus B2 as our last dimension. And let's see if we linearly transform these vectors separately and then add them up and check if we will get the same answer. We have linear transformation of A, linear transformation of B. We have 2A1 plus A2, A1 minus A2, plus we are adding them up. We have 2B1, B1 plus B2, B1 minus B2. And as you can see, when we add these vectors, we get the same result. We add 2A1 and 2B1. This gives us 2A1 plus 2B1. We get A1 plus B1 plus B2 plus B2 as the Y dimension, or the Y value. For Z, we get A1 plus B1 minus A2 minus B2. And this is also the same, so we can conclude that this mapping above is additive. And homogeneity, this is about multiplication. If we have the vector V and we multiply that vector with a scalar value and then linearly transform it, it must be equal to the linear transformation of V and then scaling later. So when you scale shouldn't matter. When you are doing linear algebra, you can scale the vector first, then transform it, or you can transform, then scale. And let's see if this linear transformation is, or this transformation is homogeneous or not. And we know that this is homogeneous because we have AB, so we get AX, AY, then we transform that, we get 2AX, AX plus AY, AX minus AY. As the transform vector, we scaled first, then transformed it. Now let's look at the transformation and then multiplying with the scalar. So we transform X and Y, we get 2X plus Y, 2X, and then X plus Y, X minus Y, and this is multiplied with the scalar alpha, and when we distribute the alpha, we will get the same answer. And this is homogeneous. So our transformation is a linear transformation. Kernel is the set of vectors that map to the zero vector. For example, we have the set A and set B. Set A has the vectors zero vector VA1, VA2, VA3, VA4, and the set B has zero vector VB1 and VB2. As you can see, the vectors VA3 and VA4 map to the zero vector. So those two vectors are in the kernel. And we will do more operations with kernel once we learn about matrices. So let's start learning about matrices. They are a fundamental part of linear algebra. Matrices are a compact way of writing linear equation systems and linear transformations. Let's look at this linear equation system. We have x minus 3y plus 14z equals to 5, 2x minus 5y minus 1z equals to 3, 5x plus 15y plus 4z equals to 2, and we have 7x plus 4y plus 6z is equal to 0. We have 4 rows and 3 columns. So our matrix will be a 4 by 3 matrix. While writing your equation system as a matrix, you write the coefficients of your unknowns as your values in the matrix. So we have 1, 3, 14, and then on the right side you write your result. So 5, 2, minus 5, negative 1, 3, and the result is 3. 5, 15, 4, result is 2. 7, 8, 6, and the result is 0. They are really useful, and we will do lots of different operations with them, and they are a fundamental part of machine learning. We also have tensors. You can think of tensors as multidimensional matrices. In a matrix, the values that it holds are scalar values or regular numbers. So this one has 1, 2, 5, 7, 3, negative 5, 15, 8, 14, negative 1, 4, 6. They're all regular numbers. But in our tensor, instead of regular numbers, we have vectors. We have 1, 5, negative 5, negative 5, 2, 6, 10, and 4, 6. So this is a 2 by 2 tensor, or a 2 by 2 matrix, but instead of regular numbers, it's holding vectors. Or we could have a 2 by 1, so 2 rows and a column matrix, and this one is holding a matrix as its values. The first value of the first row is the matrix A, B, C, D, and the second row, first column, the only column is the matrix X, Y, Z, W. Here we have scalar, vector, matrix, and a tensor. Scalar has only one value. We have vector 1, 2, and we have matrix, which is created by vectors, and then we have a tensor. And as you can see, dimension is increasing one by one. And tensors are very important in machine learning. All operations are done with matrices and tensors. Logistic regression, convolutional neural networks, or q-learning algorithms all use matrix tensor operations. So you cannot completely comprehend or understand those machine learning operations or algorithms without understanding matrices and tensors first. Now let's continue with matrix operations. We have matrix multiplication. There is a fundamental rule. Number of columns of the first matrix must be equal to the number of rows of the second matrix. What I mean is that, let's say that we have A by B and B by C, and we are multiplying those two matrices, and the result will be an A by C matrix. So let's say that we have a 4 by 3 matrix and a 3 by 4 matrix. The result would be a 4 by 4 matrix, because you have 4 by 3, 3 by 4, the 4's cancel out, they don't cancel out, but you can just simply erase them and write A by C. This is a quick and easy way of memorizing this or learning how it works. Here we have an in-depth example of multiplying a matrix with a vector. We will multiply matrices with vectors first, and then we will multiply with matrices with other matrices. Once you know how to multiply a vector with a matrix, multiplying various matrices will be very easy. First of all, we have the vector xy, and we have the matrix A, B, C, D. You can think of the matrix as a linear transformation, and you might want to ask, what is it really transforming? Matrices transform the basis vectors for a space, and once you transform the basis vectors, you transform everything. So for example, let's say that the vector xy has the default basis vectors 0, 1, and 1, 0. Those 1 zeros and 0 1s becomes the vectors A, B, C, D. So we multiply x with AB, because this is what its new basis is, and we have y multiplied with CD, because it is the y's new basis. So resultant matrix is a 2 by 1 matrix. We have 2 rows and a single column, and as you can see, we have 2 by 2 multiplied with 2 by 1. You can erase the 2's that are in the middle, and the result is 2 by 1. We can multiply the vector AB with the scalar x. We get AX and XB, and then we get YC, YD, and then we add those up, we get ax plus cy as our x, or as our first dimension, and we get bx plus dy as our second dimension. And in programming, you can think of every vector as a matrix. For example, the vector AB or vector CD or the vector ax plus cy, bx plus dy are all 2 by 1 matrices. And let's say that we have another vector zw, and we do the same thing. We multiply z with AB, we multiply w with cd, and write the answer. We get az plus cy, or cw, not cy, as our first row, and we get bz plus dw as our second row. And what would happen if we wanted to multiply the matrix ABCD with the matrix XYZW? And let's do that now. Let's look at this example. We have ABCD and XYZW. As you can see, we stacked the vectors XY and ZW horizontally, and just by looking at the final answer, the resultant vectors are also stacked and combined into a matrix. We have a 2 by 2 matrix. We have ax plus cy, bx plus dy as our first row and the second row of the first column. And for our second column, we have az plus cw, bz plus dw. And if we look at the matrices that we multiplied, we have the second column, and that's zw, and the second column multiplied with the matrix is equal to that specific vector multiplied with that matrix. So while we are multiplying matrices with other matrices, we basically divide the second matrix into vectors and multiply them with the original matrix or matrix 1, and then we stack the answers horizontally. Now let's continue with range of a matrix. We will do more examples of matrix multiplication. Let's say that we have the matrix A1, A2, A3, B1, B2, B3. Range of a matrix is the all possible linear combinations of the column vectors. So you can think of the column vectors as the basis. We have A1, A2, A3, B1, B2, B3. Those are basis vectors, and any vector that we can create with those two vectors is in the span of this matrix. And this is how you write the range. We have range of M is the span of those two vectors. Let's look at the kernel of a matrix. We know that kernel is the set of vectors that become the zero vector after a linear transformation. Let's say that we have the matrix A and we have the vector V, and we multiply those two and get the zero vector. If we get the zero vector, the vector V is in the kernel of the matrix A. And let's look at the mathematical expression for that. We have the linear transformation A1, A2, A3, B1, B2, B3, and we transform the matrix XY. We multiply the first column with the X, the second column with the Y. Here we have a 3 by 2 matrix multiplied with 2 by 1, so the result is 3 by 1. We do X times A1, A2, A3 plus Y times B1, B2, B3, classic, and then we get A1X plus B1Y, A2X plus B2Y, A3X plus B3Y, and we set that equal to 0, and any X and Y that satisfy this condition for the matrix A are in the kernel of that matrix. Now let's look at a numerical example. We have the matrix 1, 2, 3, 2, 4, 6, and as you can see, we can easily reduce this matrix. We can do that by multiplying the first row with 2 and subtract that from the second row and replace that with the second row, and we get 2 minus 2, 4 minus 4, and 6 minus 6, and we write our result as the second row, and we get 1, 0, 2, 0, and 3, 0. Now it is a lot easier to work with. We can write the reduced matrix as an equation. We have x plus 2y plus 3z equals to 0. We can write our x in terms of y and z. We are looking for the vectors that become the 0 vector, and those x, y, and z values are the coordinates of those vectors. And we want them to write in the vector format, and we already have the x. X is equal to negative 2y minus 3z, and y is equal to y, z is equal to z, and then we can write it in vector format now. X is negative 2y minus 3z, y is equal to y, z is equal to z. And this is the general equation for the vectors that become the kernel. And we can separate those two vectors. We can separate y and z, and we can write that as a sum. So if we have negative 2y, y 0, and the z part is negative 3z, 0, z, if we added those two vectors, we will get negative 2y minus 3z, y, z. So anytime you are trying to find the kernel and you have different unknowns, eliminate as much as you can and then separate the unknowns. In this scenario, we eliminated x, we are stuck with z and y, then we separated those two unknowns. And after separating the unknowns, we can simply remove them or write vectors in terms of those two unknowns. We have y times negative 2, 1, 0, and z times negative 3, 0, 1. And because we are looking at a linear kernel, the vector negative 2, 1, 0, and the vector negative 4, 2, 0 are the same. They are both in the kernel because one of them is the linear scaling or scaled version of the other one. Or if we had negative 6, 0, 2, that's just negative 3, 0, 1 scaled. So while writing the kernel, we want to write linearly independent vectors. Because if we did not want to write the linearly independent vectors, we would have infinite number of vectors in the kernel. But we want to write the simplest versions, the ones that are linearly independent. We have y and z separate, those are just scalars. So we have the vectors that we want to get. The kernel of the matrix M are the vectors negative 2, 1, 0, and negative 3, 0, 1, and any scaled versions of those two vectors. Negative 20, 10, 0 is also scaled or transformed to the 0 vector, and if we scale the second vector by 200, we get negative 600, 0, 200, and if you multiply that vector with the matrix M, we would also get the 0 vector. You can think of it as a scale or a scalar times matrix times vector. The matrix times vector is equal to 0, and 0 times any number is equal to 0, so the scalar doesn't matter. And now let's continue with the determinant of a matrix. This gives us the area or the volume if we are working with three-dimensional spaces created by the basis vectors. Here we have a simple xy coordinate plane. We have the basis vectors 0, 1, and 1, 0, so the area is simply A. And let's say that we are transforming that space. Our x new is 2, 0, y new is root 2, root 2. The area that is created by those two new basis vectors is 2.8a. The y vector or the y basis is transformed and rotated 45 degrees, and we have 2 times 2 times 45 degrees, so the area is 2.8. Or you could use linear algebra method instead of geometry to find the new determinant. Now let's look at the formula for finding determinant with algebra. Say that we have the matrix A, B, C, D, a 2 by 2 matrix. So the determinant of that matrix is AD minus CB. Or if we have the matrix 2, 4, 3, 8, the determinant would be 2 times 8 minus 3 times 4. We have 16 minus 12, and that's equal to 4. And if we have a 3 by 3 matrix A, B, C, D, F, G, H, I, it's a little more complicated, but it's not that hard to find. We have A and the determinant of E, H, F, I. When we have straight bars without the shorter lines on the top, the shorter horizontal lines that you can see, if the notation doesn't have them, it means matrix. While writing on paper, it doesn't matter that much. But if you see something that's typed on a computer, and if you don't see the shorter lines, if they're not like brackets, if they're just lines, that means determinant. So we have A multiplied with the determinant of this EHFI matrix minus B times the determinant of DFGI matrix plus the determinant of DEGH matrix. That's equal to A times EI minus HF minus B times DI minus GF plus C times DH minus GE. Determinant is very useful, like can give us a lot of information about a transformation, like the eigenvalue or the eigenvector, which we will learn soon because they are very useful in machine learning and necessary to know. Now let's continue with the identity matrix. Identity matrix is the equivalent of 1 in regular algebra. If you multiply a vector with the identity matrix, you get your original vector. If you multiplied any regular number with 1, you would get that number. If you multiply any matrix with the identity matrix, you get the original matrix, or if you multiply any vector with the identity matrix, you get that original vector. And it has ones along the diagonal, and every other value is 0. And I think that makes sense. For example, we have x, y, z, and we have how much the x is changing, and we have 1, 0, 0, so the x isn't changing for the first dimension. We have 0, 1, 0, the first dimension doesn't change or scale to 0. The second dimension, y dimension is 1, the z dimension doesn't exist, and we have the 0, 0, 1, that's for the z value. So none of the basis vectors for a vector or a matrix change when you multiply them with an identity matrix. And let's learn about transposing a matrix. This is also very useful, and you will need to transpose your matrices while analyzing your data. It is simply switching rows and columns. Let's say that we have A, X, Y, Z, and A, B, C. After transposing it, we get X, Y, Z, and A, B, C. Our rows become our columns. We have XA, YB, ZC instead of XYZ and ABC. And we also have inverse matrices. A matrix times its inverse is equal to the identity matrix. So if we have the matrix A and we multiply with A inverse, then we get 1. The identity matrix 1, then 0, 1, and then 0, 0, 1 as the rows. And this is the mathematical expression for finding the identity matrix. If we have matrix A as AC, BD, and then its inverse is 1 over determinant of A multiplied with dA and then negative C, negative B. As you can see, while writing our new matrix DC, D negative C and negative BA, we replaced or changed the positions of A and B, and also multiplied C and B with negative. And there is another important thing you can see here. We have 1 over determinant of A, and 1 over 0 is undefined. This means that if the determinant of a matrix is 0, we cannot take its inverse. And this also makes sense because if a determinant is 0, then this means that the matrix is just a line, and this is what we call a singular matrix, and you cannot take its inverse because when you have a singular line only, you wouldn't be able to find anything or any matrix that would equal to the identity matrix. And this is why we find inverse of a matrix. We cannot divide matrix A by matrix B. We have matrix addition. We can add matrices, we can subtract matrices, but we cannot divide matrices. We can multiply them. So we get the inverse of matrix B and multiply matrix A with inverse of matrix B, which gives us the same result. Think about regular numbers. If you have, for example, 1, or not 1, but let's say that you have 5. If you do 5 to the power of negative 1, you get 1 over 5. And multiplying A by 5 over negative 1 is the same as dividing A by 5. In both scenarios, you get 1 over 5. And this is why we find an inverse matrix. Here we had the pseudocode for radian basis network function. And while calculating the weights, we use matrix multiplication, identity matrix, inverse matrix, and transpose matrix. As you can see here, with transpose, multiply identity and inverse. And we also compute gradients, which will be taught in our calculus or machine learning course. And now we have the eigenvalue and the eigenvector. When transformed, eigenvector's span doesn't change. The vector's length changes by a factor, which is called the eigenvalue. Here we have the vector v and the matrix A, and we are transforming that vector v with that matrix A, and our result is the eigenvalue times the vector. So the vector itself doesn't change, it doesn't rotate, it only gets shorter or longer, and sometimes there is no difference. The eigenvalue is simply 1. And we can find that specific eigenvalue for every matrix. And after finding the eigenvalues, we can find the eigenvectors. And let's write that eigenvalue in matrix form, because we have a matrix times a vector and a scalar times a vector. Instead of that scalar, we need a matrix, and we can simply use the identity matrix to get a matrix that would be the same as multiplying our vector with that scalar. So we multiply our identity matrix with the eigenvalue, and we can write it in brackets. We have matrix A times vector v, and we have matrix identity and eigenvalue. And for example, for a regular vector with 3 dimensions or space with 3 dimensions, our identity matrix would be 1, 0, 0, 0, 1, 0, and 0, 0, 1, if that is 3 by 3. And we can write lambda 0, 0, 1, not 1, 0, lambda 0, and 0, 0, lambda. And multiplying that with our vector would give us the same answer. Because when we multiply the vector with the identity matrix, we get the vector, and then we multiply with the eigenvalue. And you know that while multiplying things, if we change the order, final result doesn't change. And we want to get the specific eigenvalues. So our next step is writing the matrix times vector minus lambda times the identity matrix times vector is equal to 0. This is perfectly fine mathematically, there's nothing complicated with that. And then we can write everything in terms of v to get our specific matrix. So we have A minus the matrix lambda identity matrix Now we have a matrix on the left side as well. We have matrix A minus lambda identity matrix times V is equal to 0. And you can see that if our vector is a 0 vector, it will always equal to 0. But we want the eigenvalues when the vector is not equal to the 0 vector. And when you visualize this, this is the same as squishing a vector to one dimension or a space into one dimension. The first one, A minus lambda identity matrix. And when we have only one dimension, a singular line, we know that the determinant is equal to 0 because we squish the vector to one dimension. And now the determinant of the matrix A minus lambda I is equal to the 0. And we know how to find the determinant, so we can use that to find our eigenvalues and then the eigenvectors. Let's look at a mathematical example. Let's find the eigenvalues and the eigenvectors of the matrix 4, 5, 3, 2. We do the matrix A. We are doing this third step here, or you can look at the last step. We get our new matrix and we subtract the identity matrix times lambda. And when we have a 2 by 2 matrix, our identity matrix is 1, 0, 0, 1. 1, 0, 0, 1 times lambda is lambda 0, 0 lambda, and 4, 5, 3, 2 minus lambda 0, 0 lambda is equal to 4 minus lambda 5, 3, and 2 minus lambda. And we know that the determinant is equal to 0, so we can find our lambda values, our eigenvalues. We know how to find the determinant. We multiply the diagonal values and then subtract them. We have 4 minus lambda times 2 minus lambda minus 3 times 5. Doing this math gives us negative 1 and 7 as our eigenvalues. And from those eigenvalues, we can find our eigenvectors. Because we know that if we put our eigenvalues into the matrix above and multiply any vector xy with those values, the result will be the 0 vector. Let's do it for negative 1. We have 5, 5, 3, 3, xy. We got these numbers by plugging negative 1 for our lambda. Then we have 5x plus 3y equals to 0, and from that we can write 5x is equal to negative 3y, and our y is equal to y, our x is equal to negative 3 over 5y, and the same as what we did in span, we can take the y out, then we get negative 3 over 5 and 1 times a scalar that doesn't matter. Any scaled version of this vector, and if you transform that by a vector or the matrix, you would also get an eigenvector. Scaling this vector doesn't matter, and we have our second eigenvalue. We have lambda that's equal to 7. We do the same thing. We plug 7 into the matrix. We get negative 3, 5, 3, negative 5, xy equals to 0, 0, and then we get x is equal to y, so we get 1, 1. And if we plug 2, 2 or 3, 3 as our x and y's, we would also get 0, 0. So any linear combination of the vector or any scaled version of the vector 1, 1 is also our eigenvector, but we want to write the simple ones. Writing only 1, 1 works. We want a set that's linearly independent as our set of eigenvectors. We use eigenvectors while doing feature extraction for principal component analysis. We lower the number of features if we have too many, and the eigenvector with the biggest eigenvalue is the principal component. That was the end of our linear algebra course. We didn't cover all of linear algebra. There is much to learn, but what you have learned in this course should be enough for learning more about artificial intelligence and machine learning. And you can find other online resources to develop yourself even further, and then it will be easier for you because you are familiar with the concepts. I will show you some other resources and courses, and all the links are in the description of this video. These are our Python and data science courses. You can find both of them on Udemy and watch them to develop yourself on the field of artificial intelligence and machine learning. You should finish the Python course first and then learn about the data science and Python course. Please follow us on social media. We have LinkedIn, Udemy, a website, Kaggle page, GitHub. You can see our contact information. You can email us any question, whether about math, programming, or career choices. Please subscribe to our YouTube channel. And here we have more resources about machine learning and linear algebra. And you can look at these links to develop yourself even further. This is all for now. See you in other courses. Hello everyone. Welcome to Calculus for Data Science and Machine Learning with Datai. In this course, we will cover what's calculus, applications of calculus in machine learning. We will cover a specific calculus topic, and then we will look at where it is used. Calculus notation. We will look at different types of notations like the Leibniz notation or the Newton notation. And we will look into computation maps, linear function, derivatives. Derivatives is very important for calculus, and it's basically half of it. You can't apply or use calculus without understanding how derivatives work. And methods of taking derivatives like product rule and quotient rule, exponential and logarithm rule, sine and cosine functions, sigmoid function, hyperbolic functions, and we'll continue with chain rule and differentiation. Differentiation is another name for taking the derivative. Multivariable functions and partial differentiation. Differentiating a function is the same as taking the derivative of a function. Segment notation, Taylor and Maclaurin series expansion, they are very similar, and they are how your calculators or your computers analyze functions. Then we will continue with integration. Integration is basically the opposite of differentiation. And area between curves, distance measurement, argmax and argmin. Let's answer the question, what is calculus? Simply, calculus is the study of change, and the change can be change of anything with respect to anything. And a common change is change in velocity or position with respect to time. For example, let's say that you are driving, and because you are moving, your position is changing every second, so you can analyze how your position changes with respect to time. If you take the first derivative of your position time function, you will get your velocity time function. And if you take the derivative of that, you will get acceleration time. So acceleration time graph or the function shows you how your velocity is changing every second, and velocity time graph showing how your position is changing every second. You can go from one to another by using integration and differentiation. Here we have Newton's second law of motion. We have F is equal to ma, and instead of acceleration, we can write d squared h over dt squared. This means we have a function that's with respect to time, and we have h is the height or position, and we are taking the second derivative of height with respect to time, and this is giving us acceleration. And calculus is very common in every area of physics. If you are doing electricity and magnetism, or springs, or chemistry, math, computing, anything that you do that involves some change, calculus is used. Here we have four general applications of calculus in machine learning. We have gradient computation, and to find a gradient we use differentiation. And we have numerical optimization, which also uses differentiation techniques. And we have Bayesian methods, which require integrals. And we have variational inference and related techniques. These also use calculus because we need calculus to approximate functions. We have calculus notation here, and there are different ways of showing your notation. For example, we have this first derivative here. You can write dy dx, or you can write y and just add this y prime or y double prime for second derivative, or you can write this second derivative. These are the same thing, or you can have nth derivative of y, or you can write dn and y and dxn. And if you are taking derivatives with respect to time, you can write y and dot or y two dots. This is more commonly known as Newton notation because he is the person that used calculus mostly for analyzing how something changes with respect to time with his laws of motion. And here we have the integral sign. We have single integrals, double integrals, and triple integrals. And we have the partial derivatives. So if a function is taking two inputs, we can only differentiate with respect to one input at a time. So we have this function that's having x and y as the inputs, and here in this example we are taking derivative with respect to x. We have a computation map here, and we have x, y, and z as our three variables. To get a, we add x and y, then we add z to that a value and get b, and finally we multiply that b variable by 2 to get c as our final output. This is an example of a computation map or a computation graph, and they are an easy way of thinking about mathematical expressions. We are visualizing mathematical expressions so we can understand them better. Here we have the computation map for logistic regression. We have our 4096 inputs X terrain, and we have a weight that's corresponding to each input or each terrain, each p-value, and then we are summing all of them up. But before summing, we multiply them with the weights, and then sum everything up, and then add our bias. So we are doing px1 times p0, px2 times v1, px3 times v2, and px 4096 times weight 4096, and then add our bias. And this sum gives us the z value, and we put this z value through a sigmoid function to get y hat, and output is the probability. Instead of writing z like this, we could write z is equal to terrain times weights plus p, and this wouldn't make as much sense. Visualizing it like this is easier for everyone. We have two types of functions. There are linear functions and nonlinear functions. Linear functions are functions that are both additive and homogeneous, and the output of the function is a line. As you can see here, we have a segment of a linear function, and they are very important for machine learning and data science, and there are so much more to learn about them other than calculus. So to learn about linear functions, you should check out our linear algebra course, because that's where we teach linear functions in detail. Here we have example of a linear function. A line is fit through data points, and this is example of a linear regression algorithm. We have multiple data points, and we find a line that fits the data the best, and then write that line as a function of y and x. This method is one of the fundamental algorithms in machine learning. Let's start learning actual calculus now. Here we have the derivative formula. Let's say that we have a function f and it takes in the value x, and we have dy dx. This is the derivative notation. You could write f prime x instead. It doesn't matter what you write here. Just know that this formula gives you the derivative of any function, but you won't use this derivative formula because there are easier methods to find derivatives of every function, and they are very easy to memorize. But we will do examples of this formula too, so you can see how it works. We have limit of h as it goes to 0. We take f x plus h minus f of x over h. As you can see, we have fx and negative fx. Here, this function is shifted by h value, and then we subtract the shifted function from the original function and divide it by h as h approaches 0. As h gets infinitely small, so when we take the derivative, we look at the slope or the gradient at a very small point, at a instant, at a single x value. And now let's apply this formula on this linear function. We have y is equal to f of x is equal to 5x plus 3. We have dy dx, or the derivative, and we have our formula, and then we just write our formula here. Instead of x, we put x plus h plus 3 as this function here, and this is just regular x, so negative 5x negative 3 over h as h approaches 0. And don't worry about this h here. Eventually this h will cancel it when the value is up here, and it does this every time, so you don't actually divide something by 0. Here we have 5h plus 5x plus 3 minus 5x minus 3. This gives us 5h of h, and this is equal to h, not h, 5. As the h's cancel out, and taking the derivative of a linear function, is it necessary? Because when you have a linear function, the derivative is always equal to the coefficient of x. As you can see here, when x is 0, or not 0, let's say that our x is 5, no, 0 is actually a good value. We have x is equal to 0, then our y value is equal to 3, and if we write 1 as our x value, the y value becomes 8. So when x changes by 1, y is changing by 5. If you put 2 as our x value, we get 13, and that's 5 more than 8, and etc. So when you change the value of y by 1, you change the value of, when you change the value of x by 1, you change the value of y by 5. So if you put negative 1 instead here, you get negative 1, negative 5 plus 3, negative 5 plus 3 is equal to negative 2. And let's do the same for a quadratic function. We have y is equal to x squared, negative 3x plus 5, and we apply the same formula. Dy dx is equal to the limit of, as h goes to infinity, f of x plus h minus f of x over h. And we plug the formula here. We plug this value to this function, x plus h squared minus 3x plus h plus 5 minus x squared plus 3x minus 5. We get rid of this parentheses and this parentheses and get x squared plus 2hx plus h squared minus 3x minus 3h plus 5 minus x squared plus 3x minus 5 is equal to limit, or the derivative. This is going to be 0, and as you can see, when we do the algebra, here we get 2hx plus h squared minus 3h over h, and we can cancel all the h's here. So this cancels with this cancels with this cancels with this, so there is no h here, and we simply get 2x minus 3 as everything cancels out. We have 2x minus 3 plus h, but because the limit is approaching 0, this h is cancelled, and this is our derivative. And here we have the shortcut. Let's say that we have y is equal to axb plus cx to the power of negative d, and when we take the first derivative, we get abx to the power of b minus 1 minus cdx to the power of negative d negative 1, or minus d minus 1. And as you can see, this value goes here, this value goes here, and then you subtract 1 from both of them. And when we look at this one, this value went here, and we subtracted 1 here, so it becomes 2x, and this is 3x to the power of 1. 1 goes here, and we subtract 1, so this is 1 times 3 times x to the power of 0, which is equal to 3. And we have 5x squared plus 3x minus 1 over 3. This goes here, and 10 minus 1 from this one, just x to the power of 1. This goes here. 3 times 1 over 3 is 1, and then negative 1 over 3 minus 1 is equal to negative 4 over 3. Now let's continue with product rule. We use this rule when a function can be written as the multiplication of two other functions. For example, if h of x is equal to f of x times g of x, then the derivative of h would be derivative of f times g of x plus the first derivative of g of x times f of x. Now let's look at an example. Let's say that h of x is equal to x squared minus 3x plus 5, our first function, times 5x plus 3, our second function. And instead of multiplying those two functions, let's use the formula above. We have 2x minus 3 as the first derivative of x, f, and 5 is the derivative of g. And then plug them into the equation. We get 2x minus 3 times the derivative 5x plus 3 and 5 times x squared minus 3x plus 5. And after doing the algebra, we get 15x squared minus 24x plus 16 as the first derivative of h. And instead of using product rule and multiply the functions, you would get the same answer. We need to know product rule because in some functions we cannot multiply the functions. For example, let's say that we have e to the x times sine x. We wouldn't be able to take the derivative of that h function the regular way. We would either need to use product rule and other rules, or use the derivative formula that we used, the one with the limits. And we also have the quotient rule. This is the opposite of the product rule. Instead of multiplying two functions, we have h of x is equal to f of x divided by g of x. And h prime, or derivative of h of x, is equal to g of x times f of x, the bottom function, times the derivative of the top function minus, instead of plus, g of x, the first derivative of that, times the f of x, and then divided by the square of the bottom function. So let's say that h of x is equal to x plus 2 over 3x plus 1. And we can take the derivatives as 1 and 3. They are simple. We have 1 times 3x plus 1 minus 3 times x plus 2 divided by 3x plus 1 squared. This gives us minus 5 over 3x plus 1 squared. It's really simple, and you can write other functions to try it out. Now let's continue with exponential rule. Let's say that f of x is equal to e to the power of g of x. Then the derivative of f of x is equal to the first derivative of g of x times e to the power of g of x. As you can see, this here stays the same, and you just add the first derivative of whatever this function is. For example, if we have e to the power of x squared minus 3x plus 5, we keep this part the same and multiply it by the first derivative of this function, which is 2x minus 3. So our f prime x is equal to 2x minus 3 times e to the power of 2x squared minus 3x plus 5. There is also a rule for logarithms. Let's say that h of x is equal to ln of or natural log of f of x. Then the derivative of h of x is equal to 1 over the function that's inside the logarithm times the function's derivative. For example, if we have ln 3x plus 1, our derivative is 1 over this fx times its derivative. We have this function here, and its derivative is 3, so 3 over 3x plus 1. In neural networks, there is a loss due to forward propagation, and we find that loss by using this function that you can see here. And as you can see, we are using the logarithms here. We have log p yi and log 1 minus p yi, and to be able to use this function properly, you need to know how logarithms work and the possible mathematical methods that you can apply to them, like how they would interact with integrals or derivatives. This binary cross entropy function is one of the most important functions in machine learning, so you have to know logarithms as well as this function. And now let's continue with sine and cosine functions. Let's say that we have the sine function, we have h of x, and h of x is equal to sine f of x. Then the derivative of h of x is equal to cosine f of x times the derivative of f of x. For example, if we have sine x squared, our f of x is x squared, then our hx will be 2x times cosine x squared. This part stays the same, the sine becomes cosine, what's inside the brackets is the same, the angle is still x squared, but the overall result is multiplied by this value here, or not the value but its derivative. And with cosine it's the same, cosine function becomes negative sine. Here sine becomes cosine, but here when we have cosine of f of x and taking the derivative of it, we get the derivative of the function times sine f of x, but there's a minus sign here. So if we had sine x, for example, it would become cosine x, but if we had cosine x, it becomes negative sine x. Here we have h of x equal to cosine x squared, and we take its derivative, we get h of x, or h prime of x, equals to negative 2x, derivative of this value, and sine x squared. This is all for sine and cosine. The important thing here is not dropping this negative value. Now let's look into sigmoid functions. As you can see here, we have an example of a sigmoid function. We have 1 over 1 plus e to the negative z, and as z approaches infinity, you can see that it is reaching 1, and as z approaches negative infinity, it is approaching 0. For example, if you put negative 50 here, we would get 1 over 1 plus e to the 50. So this part would be so great that this whole equation would be practically 0. And if you put, for example, positive 50 here, we get 1 over 1 plus e to the negative 50, which is practically 0. Then we get 1 over 1, that's equal to 1. And sigmoid functions are highly used in machine learning. They are used as the output layer in binary classification for neural networks. And in the previous slides, when we had the computation map for a regression algorithm, we used the sigmoid function to get our output. Now let's continue with hyperbolic functions. As you can see, hyperbolic function looks similar to the sigmoid function. As you can see, this function approaches positive infinity when the x is increasing, and it approaches negative infinity when the x is decreasing. If we have x is equal to 10, we have e to the power of 10 minus e to the power of negative 10, which is practically 0. So we get e to the power of 10 over 2, which is a huge number. And if we have x as negative, we get e to the power of negative, for example, 10. This is practically 0. Then we get negative e to the power of, double negatives cancel out. We get e to the power of a value, for example, 10, and negative, so it's approaching negative infinity. These hyperbolic functions are used as activation functions in neural networks, and these activation functions increase nonlinearity, and they are very important for machine learning in general. Now let's continue with chain rule. Here we have fx, capital F, and let's say that this x value is equal to g of x and fx. So the input for the function f is the output for the function g. So this function's value depends on this function. So when we take the derivative of f, we take the derivative of what's inside, and we also take the derivative of this general f function. And this is another way of writing chain rule. We have dy, dx, and we have dy, du, and du, dx. We have different functions, and we take y's derivative with respect to u, and u's derivative with respect to dx. And then when we multiply those derivatives, we get how y changes and the x changes. These are showing the same thing, but it's hard to comprehend just by looking at it, so let's look at an example now. Here we have the outside function. This is our f, and we have x squared plus x. This is our g of x, and to get the derivative of this function, we take the derivatives of both functions. So we take the derivative of our function f, that's the cosine function, and we also take the derivative of g, that's x squared plus x. Cosine becomes negative sine x, as we learned in the sine rule, and x squared plus x is 2x plus 1, and then we use this formula here. We have negative sine, this f prime, then we write gx as is, so we have x squared plus x multiplied with the derivative of g of x, which is 2x plus 1. Backpropagation is how neural networks learn, and they clearly use chain rule here. We have dl dz and dz dx. So we look at how L changes when Z changes and how Z changes when X changes. And then when we multiply these, we can see that the Z's cancel out and we get dl dx. For Y it's the same. we have dl dz, dz dy, z's cancel out, and we get dl dy. Implicit differentiation is the way of differentiating more complex functions. For example, x squared plus y squared is equal to 3. This is not like the functions that we have seen so far. We had y is equal to something or fx is equal to something. But here, y is on the same side as x and it is equal to a value. If we wanted to differentiate this function, we would need to use implicit differentiation. When we differentiate something, we differentiate both sides of the equation. So we differentiate x squared plus 2x squared plus y squared and also 3. Here we are differentiating both sides by x, so d by dx, and this d we will add y here and the other values. As you can see, we got 2x, this is the differential of x squared, power goes here and power minus 1, so this is 2x to the power of 1 or just 2x plus 2y. As you can see here, we treated this as a regular variable like x and wrote 2y. But when you differentiate y with respect to x, you also need to add dy dx. And if we look at the other examples, we had y that's equal to some function of x. And when we differentiate y with respect to x, we get y to the power of 0 and we add dy dx. So dy dx is equal to x something. And here, because we have y to the power of something, y doesn't disappear, it just gets a coefficient. And we can do some algebra and get dy dx is equal to negative x over y, and this is a differential equation. Let's look at another example. Let's say that we have 3xy plus y squared is equal to 5. We use the product rule and we differentiate everything by dx. When we differentiate 5, we get 0, and we get 2y dy dx when we differentiate y squared. For 3xy, we need to use product rule. So we have 3 times x times y and differentiating the whole thing. Here we can write them in brackets. We can differentiate 3 as a part of x or y. It's a coefficient, it doesn't matter. And when we use the product rule, we get 3y plus 3x dy dx. When we differentiate y, we get dy dx. And when we differentiate x, we just get 3. So 3 times y. So we get 3y plus 3x dy dx as the differential of the first part, 3xy. And then when we add this one with 2y dy dx, we get 3y plus 3x dy dx plus 2y dy dx is equal to 0. Then we can write it as dy dx is equal to 3y over 3x plus 2y. We got this by differentiating this with product rule. We got 3y plus 3x dy dx and added with this. And here we have y prime or dy dx as a function of y, which is also a differential equation. But for now, we don't need to solve how to find differential equations, so you can leave it like this. And we also need to find max and min points. This is very important for machine learning. It's also very simple. We have the graph for the function 5x squared minus 3x cubed plus x plus 1. And as you can see here, the slope is changing here and here. Let's take the differential. and we set the first derivative equal to 0, the derivative gives us the gradient, and the gradient is 0 when the line is horizontal. And here the sign of the derivative is changing. So at max and min points are the point that it goes from negative to positive or positive to negative. So here the gradient line is a straight horizontal line for both min and the max. This is why we set the first derivative equal to 0. Then we get 10x minus 9x squared plus 1 equals to 0. And then the x values that satisfy this are negative 0.092 and 1.203. This is the one here, and this is the one here. We can see their mins and maxes by looking at the graph, but how would we know if we didn't have a graph? We will look at how it changes the sign of the first derivative. So this is our derivative. These are the points that we want to check. And we'll look at how the gradient changes at these points. So here, the gradient is negative, and here, when we put 0, we get a positive number, we get 1, and if you put negative 10, this negative becomes positive. We have 100 times 9 is equal to negative 900, so this is negative 100, so our derivative is clearly negative. So here it goes from negative to positive, it is decreasing here, and then it reaches the minimum and then starts increasing. So we know that this is our minimum point. And for this value, if you put 10 here, our value goes from positive to negative. So negative, positive, negative. It is increasing up until this point, but the rate of increase is decreasing. Here it becomes 0, and it becomes negative. So we can say that this is a maximum. When the first derivative goes from negative to positive, it's a minimum. When it goes from positive to negative, it's a maximum. And this is very important for machine learning. We have local maximum here, and we have a local minimum here. And every function has local maximums and global maximums. Sometimes functions like these ones have only one min and one max, but they may have multiple minimums and multiple maximums. The smallest minimum is the global minimum, and the greatest maximum is the global maximum. And the only way of finding these points is finding every single maximum point and every single minimum point, and then writing them on a table and comparing, or you can just write code that does this for you. Finding the global minima is important for neural networks because we want that point for our neural network to work. Because of this, we need to know how to take the derivative and find the minimum points. Now let's continue with multivariable functions. Functions can have multiple inputs, not just one. For example, z may be equal to a function of x and y. For example, here we have the graph for the function f of x is equal to x squared plus y squared. The output is dependent on multiple inputs, and when graphed, we get a multidimensional space. We have the x-axis, y-axis, and the z-axis that's a result of them. When we had x and y, it was only a single line, but now we get an area here, or a sheet that's folded, and because it's folded, we can also find volume. Now let's continue with partial differentiation. This is how we take the derivatives of functions with multiple variables. We cannot take the differential with respect to multiple variables at the time, so we have to take the differential with respect to one variable and take the others as a constant. For example, we have f(x) and y is equal to x squared plus 2xy minus y squared, y cubed. And here we have this x here. This means that we are taking the derivative with respect to x. So we assume that y is a constant, like a 5 or 3 or 1, a regular number. So we get 2x and 2xy or 2yx. Take the derivative, we get 2y. And because this is a constant, its derivative is 0. And when we take the derivative of the function with respect to y, we get, this is 0, 2x, we get it from here, minus 3y squared. And we can also take the derivative with respect to both of them in different orders. We can take the derivative with respect to x then y, or y then x, and for every function this holds true, f of x and y, and when we take the derivative with respect to x first then y is the same when we take the derivative with respect to y then x. Here, as you can see, when we take the differential with respect to y here, this is a constant, so we just get 2. And when we take the differential with respect to x here, this is a constant, so we just get 2. And you can try this with multiple other functions. Here we have an example for it. We have a function and its graph is this shape you can see here, and this line has a slope on the x quadrant. Here we are looking at it from a 3D space, but this line is on the z and x plane, so at this point y is considered a constant. And if we looked at the derivative with respect to y, it would be on zy plane, x values on that line would be a constant. In neural networks, if we have multiple features, we get multiple dimensions because we have more inputs. So to get the global minimum, we use partial differential. Here you can see that to find this lowest point here, we take the derivative with respect to both x and y. And we have another example here. We want to find the absolute smallest point, and we go to only one of the axes here. And we are also getting a linear point by graphing it here. We can translate 3D spaces to 2D if we ignore the change in one dimension. Sigma notation is used to add multiple values. This value 4 shows how many values we are adding. This n is equal to a. This gives us the first value of a, and this is what we are adding, f of n. So if we have n is equal to a here, this is the value for the first index, so we add f of a, then a plus 1, a plus 2, a plus 3. For example, if we simply have 4 values, initial value is equal to 1, and we are adding n's, so we get 1, the second n is 2, 3, 4, and this gives us the sigma notation for this value here. And sigma notations is very widely used in mathematics. In machine learning, the learning process is updating the parameters, and to update our parameters we use the sigma notation, as you can see here. We have this equation and we have the sigma notation here. Our initial index is 1, so this initial value of I is equal to 1, and it ranges up to n. Taylor and McLaurin's series expansion is used to approximate functions so that our computers can analyze those functions. Let's say that we have a function of x, and that function would be equal to this result of sigma notation here. And as you can see, we have infinity here. But we know that we cannot calculate infinity with our calculators. We don't have infinite data. So we approximate. We don't get the same function, but we get very close that it's practically the same. And we start from 0 from beginning. This is how many derivatives we take. As it goes to infinity, we are taking infinite derivatives. And we have an a value. A is the center value, the value that the function is centered at, and a is 0 for Maclaurin series. And we have x minus a to the power of n over n factorial. And because we have 1 over factorial here, as you can see, as this goes to infinity, we have something over infinity here. So as we go further towards infinity, this gets smaller, but we get closer to our initial function. And let's look at an example of how this works. So let's say that we have f of x is equal to e to the x. This is very easy to take or find the approximation of, because derivative of e to the x is equal to e to the x. And let's just use our formula. And our a value is 0 because we are finding the Maclaurin series. F of x is equal to f of 0. The initial n is 0, so this is 0, this is 0, so we just get the initial value centered at 0. We have f of 0, so e to the 0 plus the first derivative, that's also e to the x, times x, plus the second derivative, x squared over 2 factorial, third derivative, the value is 0, the input value, x cubed over 3 factorial, and we just have x's here because our a value is equal to 0. And we know that e to the 0 is equal to the first derivative, the second derivative, the original function, and to the nth derivative. And its value is 1, so we can just write 1 instead of these functions here. So we get e to the x, or f of x, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And you can see the pattern here. We have x to the n over n factorial, starting at 0. When n is equal to 0, this is 1, this is also 1. 1 over 1 is equal to 1. And then we put 1 here, we get x over 1 factorial. Then we get 2 over 2 factorial, so 3 over 3 factorial. So this is n, and this is also n. This is how your calculators find the e value, that's equal to 2.71 approximately. The more terms you write here, the more accurate it gets. And now let's take a look at the graph of e to the x and compare it with the graph of this function we wrote here. We have e to the x as the red line, and the approximation with the first 4 values as 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And up until this point, we can see that it's fairly approximate. This is almost the same, and at this value, it becomes different. And if we had more points here, it would be even more accurate. Taylor and Maclaurin series work by matching the derivatives at certain points, matching the gradients. And the more points you add, the more gradients that you match. And as we have infinite values in our definition here, we get infinitely close to this function And when we get infinitely close to something, we assume that they are the same. For example, if we had 0.9999 to the infinite, we would assume that that's equal to 1, because eventually that difference would be so small that it would be practically the same. Integration is the opposite of differentiation, so the result of integration is called an antiderivative. And differentiation gives us the gradient of a line, or gradient at a certain point, like this. And integration gives us the volume under 2 points, or under a curve. There are two methods for finding the integral. You can find the integral horizontally or vertically, but 99% of the time you would find the area vertically like this. As you can see here, as we add more vertical lines here, more columns, and more columns with smaller width, we get closer to the actual area. And because of this, integration assumes that there are infinite number of infinitely small lines, and when we add everything up, we get the volume, or the area that's under the function. And when we have multidimensional spaces, instead of area, we get the volume. The volume, or the area, the result of integration can be negative, and graphically it's negative if it's under the x-axis. When you differentiate a function and integrate it, you get the original function. Let's look at the notation for integration. We have the upper limit, lower limit, and the function that we are integrating, and integrating with respect to dx. If the function was in terms of x and y, we would integrate with respect to one variable down to other variable, and we would have limits for both of the variables. Let's look at the integral of a simple function like x to the power of a. We know that when we take the derivative, we lower the power by 1 and multiply it with the power itself. So when we take the integral, we do the opposite. We add 1 to the power and divide the whole function by that power. What I mean is that we have 1 over a plus 1 times x to the a plus 1 plus a constant, because if we had a value like 5, when we take the derivative, that 5 value would be lost. So when you take the integral of a function that you don't know, it's called an indefinite integral, you have to add a constant value, and you cannot find it unless you are given initial conditions. Let's say that this value is an integer, or a real number that's independent from x. It's a constant coefficient. When we take the derivative, this becomes 0. A plus 1 minus 1 is a, and this goes here as a multiplier. They cancel out, so we get x to the power of a when we differentiate this. And as I said earlier, c is a constant that disappears when the first derivative is taken, or any derivative. And there are methods for integrating complex functions. For example, if we have u dv, I will show an example soon. This is called integration by parts. We integrate this part and this part. We divide our function into u part and dv part, and use this formula to find the integral. And this is the order that you choose your u as. If you have a log, you should probably choose that logarithm as u, or inverse, algebra, trig, and finally exponential. This doesn't make sense, so let's look at an example now. Then it will be clearer. Now let's find the integral for this function. As you can see here, we are multiplying x with e to the x. So we cannot simply write something to the power of something and add the coefficients. We need to use integration by parts. And we have our formula here, and you can memorize this as super voodoo, because this sounds like S U is equal to dV uv minus S and du. Or you can use any other method that you want to memorize this, but you should be familiar with this equation. Now let's choose our u and dv. Let's say that this is algebra, so we choose it as u, and e to the x will be our dv term. And our dv term is not just e to the x, it is e to the x dx. And let's first find our u and du that we need here. Our u is equal to x. We take the differential of both sides, so we get that du is equal to dx, which we will need here. And then we have our dv value. Our dv is equal to e to the x dx. We can integrate both sides, and when we integrate dv, we get v. When we integrate e to the x dx, we get e to the x. And then we plug them into the equation. Here we have x e to the x, this value, and this value, u and v, and v du. Our v is e to the x, and du is equal to dx. And from this we get x e to the x, this is the same, and when we integrate e to the x, we get e to the x, but minus, and we add a coefficient because we don't know if there is a value or not. So to get all the possibilities, we must add this coefficient here. And this is the second method of finding integrals. This is substitution method. This is the complex formula, but I will show you how to apply this. We have f, and inside f we have g to the x, and this f is multiplied with the derivative of g to the x dx. Now let's look at an example. This is a very similar example, and most of or all of the functions that you can use substitution, you can also use integration by parts, but in my opinion substitution is shorter, so try substitution, and if it doesn't work, try integration by parts. We have to pick a u value to substitute, and our u will be x to the power of 3 or x cubed. Then we get our du. We differentiate both sides. Du is equal to 3x squared dx. And then we find our dx value. Dx is equal to du over 3x squared. Now that we know our u and our dx, we substitute du over 3x squared as dx and substitute u as x squared. When we do the substitutions, we have this x squared here. We don't do anything with it. Instead of x squared, we put u. Instead of dx, we substitute du over 3x squared. And as you can see here, this x squared is cancelled out with this x squared. So we just get integral of e to the u du over 3. This 1 over 3 is a constant, so we can take care of it at the end. And when we take the derivative of e to the u du, we get e to the u, and we know that u is x squared, so we just replace that and add our coefficient, which is 1 over 3. Then add the constant value, because this is an indefinite integral, and when we take the derivative, this value disappears. This is to make sure that we cover every possibility. If we had the initial value, we will be able to find this, but we will leave it like this for now. And now let's use integration to find the area. Let's say that this is our function, 5x squared minus 3x dx, and we want the area between 6 and 4. And as you can see here, this is a definite integral. We know our original f of x. We are not trying to find another function. So when we take the integral, now we don't need the c value. And this is our integral. When we take the integral of 5x squared, simply we get x to the power of 3 or x cubed over 3 times 5. You can ignore this 5 and you know the integral of x squared. This is just a coefficient. And we also know how to take the integral of x. And we have negative 3 as our coefficient, but we can add that later. And then you should be able to understand this notation. We have this bar here, we have 6, and we have 4. This is the upper limit, and this is the lower limit. So we will plug 6 as our x, then 4 as our x, and subtract them from each other. Here we plug x first, and then we plug 4. We plug 6 as our x and 4 as our x. And this computation gives us 670 over 3. Getting a large value shouldn't be unexpected because we are handling with cubes here, and we have 5 times 6 cubed, which is a large number. And we can also find the area between two curves. We have f of x that's equal to root of x and g of x that's equal to x squared. This is root of x and this is x squared. And when you are finding the area between two curves, you subtract the area under one curve from the other. So the area under this curve is all of this, area under is this one, and when we subtract area under blue one from the area under red one, we get the area that's between them. This is how we construct our integral. We do 1, d, and 0. These are the points that these two curves intersect. With these functions, it's easier to find them. You can just set them equal to each other and see that they are equal to each other only at 1 and 0. If you have more complex functions, you will need to do more algebra. And then we just integrate both of the functions. You can also separate the integrals like integral of one with respect to dx and the integral of the other one, because integrals can be separated. Or you can write one function that's h of x that is equal to root of x minus x squared, and you can write 1, 0 h of x dx, and h of x is this function f of x minus g of x. And this is what we get as a result of this integral. Here we have x to the power of 1 over 2, and we have x to the power of 2. Here we have the upper limit and the lower limit. We have 3 over 2 x to the power of 3 over 2 minus x cubed over 3. And this gives us 1 over 3, and that's the area between those two curves. Now let's take a look at an example. Bayes' rule is an important machine learning algorithm. It's a probability-based algorithm, and it uses integration to find that probability. It takes in the prior probability and the likelihood, and it gives us the posterior probability. And while finding this, it finds the area under the curves, and that's integration. In machine learning, there are two different distance measurements. These are the two main ones. We have Manhattan distances and Euclidean distances. You are probably familiar with Euclidean distances. They are the smallest or the shortest distance between 2 points. We have x1, y1, x2, y2, and a direct line that goes from x1, y1 to x2, y2 is the Euclidean distance. Manhattan distance is the maximum possible sum of the distances between those 2 points. What this means is that when we get the Manhattan sum, we look at the distances between x1 and x2 and y1 and y2. And the distance from point 1 to point 2 is equal to sum of x2 minus x1 plus y2 minus y1. So we look at the horizontal difference and the vertical difference, or difference on each axis, and we add those distances up. So we have this vertical lines here as the differences in y or x, depending on your system, and we have these horizontal lines here that can be your either x's or y's, depending on how you declare everything. And we use Manhattan and Euclidean distances in various machine learning applications. Here we have the k-nearest neighbor. K-nearest neighbor is a distance-based algorithm, and while using this algorithm, we can use different distance definitions. For example, we can try to use this algorithm with the Manhattan way or the Euclidean way, and both of those different distances would give us different values because the way that they find the distance is different. We also have argmax and argmin. This is similar to the minima and the maxima that we did earlier. Argument is the input that the function takes. For example, we have the red line here, that's sine of x, and let's say that f of x or y is equal to sine of x over x. The input that the function takes is an argument, and we have argmax. Argmax, or the argument maximum, is the x value that has the highest y value. So the x value that gives us the global minima is the argmin, and the x value that gives us the global maximum is the argument maximum. And as an example, both of unnormalized and normalized sine functions have argmax of 0 because they both have their global maximum at this value of x here, which is equal to 0. We have the likelihood function here, and in this function we are trying to maximize our arguments. We have 3 arguments here. We have argmax, argmin, and our argmin here, and we want them to be the absolute maximums.